Hello and welcome back to the lab. Today on the bench we have part 2 of the Type 130 LC meter. Not LCR, just LC for inductance and capacitance. In this video we're going to run through the alignment process. As I was doing some research on what the capacitors were during the restoration video, if you haven't seen that, it's the previous video to this one, I ran across a lot of people asking for a simplified alignment procedure for this unit, and after reading through the alignment procedure I can understand why. So we're going to go through and we're going to modernize the alignment. We have some gear available to us today that was not available when this was built back in the 60s, I believe, and when the documentation was written. So for setting things like the primary oscillator, things like that, we can just use a frequency counter now, where they had to use a scope and a trigger source and a time mark generator and a couple of other things. So we'll be able to simplify that a lot finer. Now for the clock measure, or the frequency measurement, clock measurement, we're going to use my Agilent 53131A. And that's backed up by the rubidium standard, which is also linked to the GPS-DO. And before we get started, we'll check the rubidium and just see how well it's synced up to the GPS-DO. Meter we're going to pull into service for this one is the DMM 6500. That should be fine. And for some of the other adjustments, the Rigel scope, the MSO 1104 will be fine, but pretty much any modern digital scope will do. That's going to help out with the symmetry adjustments and a couple of other things. So, not too bad. While I wait for the gear to warm up and the 130 to warm up, we're going to take a look at the rubidium communications. And this is pretty much a readout of how well it's tracking and how well the atomic element is aging. The atomic element aging can be found here, this FC. This is essentially the DAC value, so that's what the digital analog converter is pulling the rubidium to. The general frequency is here, this TT. Now, that's a huge number, but that's not necessarily a problem. That's just telling me that the rubidium is running about 5 nanoseconds fast. What that number indicates is the time incident between the 1 pulse per second coming in from the GPS-DO and the 1 pulse per second leaving the rubidium. So they're off by 5 nanoseconds between the two. Now the GPS-DO is linked up to the GPS satellites and sees a bunch of them. Where I'm at, I usually am under at least 8, sometimes 15. So that clock is very stable. Nothing to worry about there. So we have a good, solid 10 megahertz reference. I'm not going to quibble about 6 nanoseconds on 10 megahertz. So we've got good clocks. All right, we have the controls set as they should be in preliminary, 300 microfarads, also picofarads. We have coarse sweep and fine sweep centered, which is what was requested. I've had the case on to let everything get nice and warmed up. So we're going to pop the case off. Now, as it says, if this is the first video you're seeing of mine, anytime you're pulling the cases... Oh, that was easy. Anytime you're pulling the cases off of vacuum tube equipment, assume there is elevated voltages. There are. Most of the B+ voltages in vacuum tube equipments range anywhere from 100 volts to 3,000 volts. So definitely know what you're looking at and what you're working with. So the first one we're actually going to measure is the 270 volt supply. We have the common lead from the meter just hooked up to chassis ground. And the 270 volt supply is going to be right there. And I need between 240 240 and 280 volts. That'll do. So actually, while we're here, pardon the camera movements. So we have a bit of ripple, 3 volts. My meter my RMS line distortion is less than 5%. It is 3.4. So 3.3 volts ripple. It's kind of high, but I don't think C401 needs to be changed. But this goes into some of the shouldn't change capacitors. It's right here in the service manual. If you change V400 and still can't get sufficient voltage, change C401. So, but we have sufficient voltage because this is only saying below 240. We have 266 with 3 volts of ripple, so that's not horrible. Also, one of the problems is I can't really bump up the capacitance too much because this has a vacuum tube rectifier, and you'll blow the cathodes off the vacuum tube rectifier if you put too much capacitance behind the tube based on inrush current. Silicon's a lot more tolerant of large temporary inrush currents. So we have to check the 150 volt line, which we pick up actually right here. Well, that'll do. I need 150 volts. What's the ripple? .200 millivolts of ripple on that rail. Let's see, do I have a ripple spec on that one? Oh, no, my ripple's fine. 120 volts ripple should be less than 12 volts peak. Yeah, no, ripple is totally fine. You check ripple in the next step. I just combined 1 and 2. Okay, my rough math says the ripple's good, but I did get a ripple spec in the service manual. So, let's check the ripple with the Rigol here real quick. This shouldn't be too hard for it. We're gonna hook this up. Ground lead. And we come in here. And we're gonna AC couple it. And we're gonna trigger off the line because that's actually what helps us lock this in. Okay, line triggering off the scope to give me a nice stable ripple waveform. We are right at our 12 volt spec, so I'm going to keep an eye on that capacitor. I'm not quite ready to change it yet, but it's either going to get a little bit better or it's going to get a little bit worse. But we are less than 12 volt spec, which is what we need to be. This is the test point 2, and the ripple should be no greater than 1 volt. Okay, our ripple there is about 800 millivolts, so not bad. The high frequency was pushing it right up to 1 volt, which is probably some of the main oscillator. So our power rails make it barely. In checking the oscillator to make sure it won't blow up the front end of my frequency counter, I set the scope to 1x. That's changed the math, so it's telling me exactly what's coming out of here. We have about a 2.5 volt signal, which is very safe for the front end of the 53131A. So what we're going to do is I have a 10x attenuator in the probe. We're going to hook this up to channel 1 on the frequency counter. We'll be able to really dial this in. So we'll just pop this from over here. So a little bit of wandering around down here is fine, but it's stable enough. I should be able to get 140 kilohertz even. So what we're going to do, let's increase the gate time a little bit. No, I want time. Give it a 1 second gate time. Actually, that's a little slow for dialing it, so we're gonna 500. Half a second. Yeah, that's good. So now I need to adjust T30 for 140 kilohertz. T30 is on the other side. It does not take much. So the inductance of my added tuning tool is about 1 hertz. So we want to be low by 1. Pull the tool off. And I need to go up by 0.3. Now I understand why they said in the manual only do it a half a turn, then one turn versus don't really throw that out of line, because that is a very, very touchy adjustment. But there's our 1400 kilohertz, and we're dithering. Millihertz on kilohertz, so not too upset with that. Well, this is as close as I'm going to get it to 1400 kilohertz. As I was watching this, taking that phone call, the oscillator kept climbing because it kept getting warmer and warmer and warmer. So I adjusted it down a few more times, but I'm really, really splitting hairs on this oscillator. So if it settles out there, and I'd also noticed that after I'd adjusted, it would climb up about 10. It would climb up about 10 hertz from where it was. So getting this dialed in took a little bit of time, things like that. But we are at 140. Now, on the factory calibration, they were at 140/70. So we got it dialed in a little tighter than that, which isn't going to be a problem. But given the thermals that were involved with this, I would give it longer than the 30 minutes in the manual that it says it wants to warm up. So I would give it an hour or two before dialing in the T30. Okay, we got to get the S30 Delta standard installed now. All right. Next thing is up. All right, controls is meter 0. So we want to bring this down to 0. Which is where we are at. The fine control is mid-range. And we need to hook up the scope again. The S30 Delta standard zeroed out when it's at 0 picofarads, 300 microfarads, and then plus 300 puff. Mid-range zeroed, and over here. And now we need to dial the scope for, we need to do adjustment 1 and dial the scope for symmetry. So I'm going to move you guys up to the scope while I dial adjustment 1. The symmetry test point is right here on this capacitor resistor combo in the LC meter. Now we're kind of cheating with the Rigol scope because we have all the measurements turned on, but we're going to do duty cycle. We're going to dial up adjustment 1 for as symmetrical a duty cycle as we can. I'm going to be happy with that right there. For doing the duty cycle measurement, adjusting the averages to a low average number, cut down on the dithering a lot, and let the scope get a better read on what the duty cycle of the waveform is. We're still in very good shape there. I wouldn't go much more over than 16 cycles or 16 averages because it would take the waveform too long to build as you're adjusting the potentiometer. Okay, the rest of the adjustments are going to be on the front end of this unit. So I have you guys. No, I need to bring the camera down a little bit. Okay, I'm going to cheat. You guys are going to help me out with this alignment. You are square on to the LC130, and I have a monitor over on the right that I can see what the camera sees. So you guys are going to get to help me do this alignment. So the first thing we need to do is we need to adjust the 300 puff range, but we need to go down to 0 picofarads, and we need to be very diligent in the meter zeroing. That's dead on 0 right there. Plus 300 picofarads. And then we need to do adjustment 2 for exactly full scale. That's going to be dead nuts on at full scale. The next thing we need to do is short circuit this, set this to 300 microhenries, and we need to 0 again. Ooh, that's at the extreme end. Okay, so this now makes sense. I had to read through this about 6 times to get this right. T1 and adjustment 2 are, they interface with each other, so it's an iterative process. So it's okay that I can't 100% zero this. What we need to do is we need to close that window in on this. So I'm going to have to do this a couple of times. It's adjust 300 microhenries, adjust 300 picofarads, adjust 300 microhenries, adjust 300 picofarads, and bounce it back and forth until it's dialed in. So I'm going to do that real quick, and we will then continue on. Okie dokie. So we're at 0. We have a very good 0 here. We're going to go to 300 picofarads, and we're hitting dead on full scale. So we're going to go down to short circuit, 300 microhenries. We can now 0 the meter, and if I go to 300 microhenries, we are dead on 300 microhenries. So We got our two 300 ranges aligned. Okay, now we got to do some of the capacitance ranges. So we go to 0 picofarads, and we want to be on 3 picofarads. And we need to 0 the meter. Ooh. Very twitchy. There we go. All right. So we're at 0 picofarads, and we've zeroed the meter out. You'll notice it'll kind of pulse like this. That fluttering is the two oscillators zero beating with each other. So then when they finally lock in, everything settles down. So that's actually normal because this has a free run. So the way this unit works is it has a free running 140 kilohertz oscillator, which we adjusted earlier. But then it sets up a tank circuit with the device under test and a few other things, and it zero beats those together. And that's how it deflects the meter and takes the measurements. So when they're not quite zero beating correctly, the needle does some funny things. But we're on the 3 picofarad range, so we're using the bottom scale, and we got to adjust 3 for a full scale reading at the plus 3 picofarad. No reason why we can't do this on camera, so we're going to go plus 3. Well, that's going to work. What's next? All right, so we're at 2.5 when we're at minus 3. So what I need to do is I need to use the fine 0 to... we're getting real close. I need to be a little square on. So what you need to do here is switch back and forth between plus 3 and minus 3 until this reads the same on both sides. But the control we're fiddling with is the fine 0. And it did say the meter will probably not be at full scale, which I can confirm. That's about as good as we're going to get it. So if we take a look, this is plus 3. That's minus 3. Plus 3. It's a little... That's about as good as we're going to get it right there. Okay, so now what we did was we zeroed out this control between plus 3 and minus 3. So now we go to plus 3, and we take adjust 3 to full scale, and that sets up the 3 picofarad range. Adjust 3. There we go, 3 picofarads, full scale. On the 10 picofarad scale, it's just zeroing out the meter, which we can see it fluttering a little bit here. And then what we're going to do is just 10 picofarad and adjust for full scale. So that one is pretty straightforward. And there's our full scale adjustment at 10 picofarad. Now what we need to do is we need to just double check the 3 picofarad range. and it's not. So what do we need to do? So we need to readjust the 3 picofarad range. Okay, iterating between the two, the 10 and the 3, I was able to dial it in a little bit better. So we're on the 3 picofarad range, and I got 3 picofarads. And if I go to the 10 picofarad range, I get 10 picofarads. And if I go to the 0 picofarads, the 0 is good on both ranges. That was a little bit of a process, just playing with these two controls, the two controls internally, the delta standard, the range knob. So getting that all lined up was kind of, it wasn't difficult, but it was time consuming and iterative. Next up is the 30 picofarad range. Okay. Needle's not jumping now, so what we need to do is, it's going to be the same process for all the ranges. Go up through the scale, check the one behind it, go up through the scale, check the one behind it, go up through the scale. So this could take a while. Having just said that, I'll take that. There's the 30 picofarad range. Just a slight tweak, and then I'll have to check the 10 again. The 100 picofarad range is a little out, so I do need to adjust that, and we'll go all the way back down and all the way back up again. Okay, after a lot of dialing and adjustments, we have gotten set. So we have a good 0 on the 3. And I'm going to do a little bit more. Okay, once more up the range, and I think that did it. So we're at 3, got it nice and stable. We'll give it +3. And it looks, and now. Okay, once more, 3 and up. So I have done this adjustment probably 12 times to get it to this point. It was very fiddly, and I'll be honest, I would not do an alignment on one of these meters without this S30 Delta standard. I just wouldn't do it. So here's 3. And we are bang on full scale. 10. Bang on full scale. 30. Looks good. 10. 100. Bang on full scale. 300 I will have to readjust to 0, which is fine. .300, and with a correct 0, we're even good down at 100 picofarads. So I finally have the capacitance ranges dialed in. The next step is to adjust the resistance compensation. So we go to 0 picofarads. 3 puff scale. Need to tweak this for a 0 reading, which is fine. Went through it. There we go. And then we want 1 kilohertz, or 1 k ohm. Sorry, not kilohertz. So we're at 8. It says near mid scale, which is right. It says adjust the 0 controls for mid scale, so we will. Right on mid scale because we can. So what we need to do now is switch to 1 meg. we are off. So I need a non-adjusting, or a non-inductive screwdriver. We'll go to our ceramics. Okay, ceramic screwdriver, since we are dealing with a capacitor right in between some oscillators, we're going to dial this to just mid-range. Right about there. That'll be good. So, what we need to do now, we need to check the voltage across the unknown component, which we're going to be looking for around a volt. The capacitor that was adjusted in the last step is sitting down here, resistance capacitor, resistance compensation in between those two tubes. Okay, checking the voltage across the unknown component. We're at 0 picofarads, and the voltage should not be more than 1 volt. It's 900 millivolts at the correct frequency, so not going to complain about that at all. So the next thing we have to do is adjust the zero control range. Jumping ahead of myself, so we go to plus 300 picofarads. And we're good there. So now what we want to do is short circuit 300 microhenries. Zero out the capacitor and 300 microhenries, and we need to get some more signal. And we're looking for a voltage under 250 millivolts, which we are, so everything is good there. I expected it to be. That was just a check step. All right, to get ready for the zero range setting, we need to pull the delta standard off. Ten microfarads. Maximum signal. .5 picofarads. So we're on the 10 scale. We are well below, so we do need to come up. That makes sense because these were almost topped out. What we need to adjust is this capacitor right here for 7.5, which will be right about here on the display, so we are pretty far off. Get our ceramic screwdrivers again. Wow, it doesn't take much to send this needle rolling. That was very out of adjustment, which is fine. So we are on the 10 scale. So it would be 6, 7 would be there, 7.5 right there. Well, I'm going to celebrate with you guys because that concludes the alignment on this LC130, which took far longer than I expected. But we have a nice accuracy unit now. One of the reasons that I really wanted one of these, the spec sheet says with careful alignment you can get a 0.5% accuracy out of this unit. So this is actually my highest accuracy LC meter that I have in the lab at the moment, followed closely by my IT28 bridge, because you can get some very good performance out of a bridge once you dial it. Now I do have a true bridge device in line for the bench. So if you're interested in seeing that, hit the subscribe button and stick around. But this is now ready for service. This will find a place up there and be ready to make some measurements for us. For me, I need this though, because I don't have a lot of UHF connections. So I need some B and Z's. The other really cool thing about one of these devices is the range can be extended significantly over the meter by putting some known capacitances and inductances in series with the inductance under, or the capacitance under measure, and using the chart that's in the service manual with this unit can go up to 10,000 microhenries of inductance, which is absolutely insane. So this is one of those tools that it's probably not going to see a lot of use on the bench, but when I need it, it's going to be the only thing I got that can do what it does, and I'm going to be glad that I'm going to be really glad that I have it. With that, if you would like a little bit more of my content, take a look at the Patreon page and see what's there. I do have some perks that I offer to patrons, time server, and a couple of other things that you can sync computers and radios and things like that to. It is a Stratum 1 time server, but that's available to all patrons. There's a DNS record to point your equipment to. Also, they are 3 to 4 weeks ahead on videos, so they'll see what's going on before YouTube does, and they are a great help to me in steering the channel and when I need to make decisions on what goes up to YouTube and what doesn't. So, with that, I'm going to close out this video. I will see everybody in the comments section in between videos. If there's something you'd like to see or me go over a topic you'd like covered, drop me a line. We'll see what we can make happen. But for now, I will see everyone in the next video. And as always, more is on the way.